yours, my friend.
I'm Phil KA9Q. You've probably never heard me on the air. I'm a guy who likes to listen and build stuff. However, I've always thought it's a worthy cause to support, so I've been a member for, I don't know, God, I last talked about this 5 years ago, so I know I'm a member at least that long. Anyway, what I'm going to talk about is a software-defined radio project I've been working on for a long time now, off and on. I'm calling it ka9q-radio for lack of a better term. What this is a set of building blocks. It's not a nice turnkey, end user system right now. I've always liked to build engines and transmissions. I don't like building user interfaces. In fact, I hate user interfaces. Somebody else can design them better than me. I like building the stuff that goes on inside. So I'm trying to find other people who come along and use my stuff as part of a larger system. And I'm to the point now where I'm actively looking for people to do that. Oh, good. Hey, this worked. Okay, so this package is it's very modular and it's multi-channel. Those are the two things that, well, actually, the multi-channel part is probably the key aspect of this thing. Most radios, including all of the SDRs that I know of, designed for hams, have really flashy user interfaces, but they really only receive one channel at a time. So I thought, okay, what can I do? I can't compete with a lot of these packages like SDR Sharp and so forth. So what could I do that hasn't been done yet in ham radio? And the thought occurred to me, well, I can build a receiver that can do lots of channels at once. And there's actually uses for that, some interesting uses for that. It also uses a mechanism called IP multicast for basically all internal communications. Those of you who know Ethernet, because you all have it in your houses, are probably already using IP multicast and don't know it. Like when you plug in a printer and then you turn on your computer and you want to go find a printer in your network, it's using IP multicast to go out and discover a printer without already knowing its address ahead of time. It's a form of broadcast, but it's a subset of broadcast. You send out a packet to a multicast group and anybody who's interested in that group can receive those packets. So one copy goes to everybody who's interested on the local area network, which makes it really interesting when you have lots of modules that are talking to each other without even making any kind of prearrangement to do that. The two types of multicast packets that I use is one for signal data, signal coming from the front end to the SDR, and then all the output data from the SDR all use the standard voice over IP protocols, particularly the real-time protocol. It's been around forever and it's a standard part of voice over IP. I've come up with my own custom control status protocol to control the front ends and also control the radio daemon. So there's two separate planes here. We usually talk in communications about a data plane and a control plane. The data plane is absolutely standard using a real-time protocol, and the control plane is something I've come up with myself, which I have documented. It, again, is based on multicast. So any control program you have sends out a multicast to whatever it's controlling, and then the responses also come back multicast, so you can actually have several control heads all watching what the others are doing. If you retune one of them, all the other ones will update automatically. Let's see. Most of the modules, because I hate user interfaces, most of the modules run as what are called daemons under Linux. A daemon is a program that runs automatically in the background. It usually starts up when you first boot the machine and just runs without any user intervention until the machine is taken down. A typical signal path, and this is just one example, there are actually many examples, because this is a very flexible way to do things, and this is how I often operate at home. I have a program called AirSpy-D, which is the program that reads from an AirSpy SDR. I have one of them right here. I can talk a little more about that later. I mean, I don't have any interest in AirSpy. I don't get any money from them. I just happen to like their products, and it's the one I'm making most use of right now. So I have a program called AirSpy-D that just reads all the data over the USB from the AirSpy, multicasts on the local area network for anybody who wants to receive it, and then the program that receives and processes that data is called radio D for radio daemon. Then the output of that comes out as I said before, real-time protocol streaming, just like voice over IP. But because that's uncompressed, it's fairly high data rate, especially when you're listening to 20 channels at once. So I have a little program called Opus D. Opus is an open source voice compression codec. It's used in a lot of places right now. It's become increasingly popular because it's open source, unlike some other voice codecs that we're probably all too familiar with. And it will automatically compress any streams that it hears and put them back out on the network so that I can listen to it, for example, over my Wi-Fi network without loading it down too much. Or I can send it over internet link, or I can actually record the compressed audio and archive it. And then the monitor program is one of the user interface programs I have running here, which actually shows all of the active multicast streams on a particular group at a given time. And I'll demonstrate that a little bit later. It's kind of primitive because, again, I don't like user interfaces. I do very simple text mode interfaces, but they're really placeholders for whoever wants to come along and do a better one. Another example of the signal flow that I use actually quite a bit is AirSpy to Radio D to Packet D, which is a packet decoder. Instead of compressing the audio so you can listen to it, it just runs a 1200 baud FSK Bell 202 modem we've had for almost 40 years now for 1200 baud packet radio. And then it goes into another program called APRS feed, which feeds that all into the APRS backbone network. So this functions as a receive-only iGate. I've had this running at Mount Carmel High School now for several years. It actually doesn't get that much use anymore since we stopped using APRS for balloon tracking and we use something else, but it's still there and it is still working. So the whole package is now fairly stable. I've been working on it for about 5 years off and on. It's open source and it's ready for developers to use. It's not, excuse me, not a turnkey package for end users with a fancy graphical user interface. This is a set of modules that other developers can come and use and build stuff around. And I think it's got some potentially interesting applications. It's all available as open source on GitHub. You probably can't read this, but it's on my GitHub account, ka9q/ka9q-radio. So I welcome people to use it. So I mentioned the AirSpy front end. There's two that I use heavily, AirSpy and AirSpy HF. If you're familiar with their products, the AirSpy is that little box over there. It tunes anywhere from about 25 megahertz to 1.7 gigahertz, I think. It samples at 20 megahertz, so it grabs about 9 megahertz of spectrum anywhere in that tuning range, and sends it over a USB to the computer that's attached to it. And my AirSpy daemon grabs that and then multicasts it out as a stream of IP packets at about 240 megabits per second, which is about a quarter of a gigabit Ethernet, but it does work. I find in practice I don't usually do that. I'm usually only consuming the AirSpy data on one computer, so I usually run it on the same computer as the radio daemon and turn off the multicasting. But I can turn it on if I want to receive it on some other computer or if I want to record the raw data coming out, although it's a very high fire hose of bits. The AirSpy HF Plus is the AirSpy SDR that's designed for HF, goes up to about 31, 32 megahertz, something like that. It doesn't sample as fast as the AirSpy for VHF and UHF, but that's okay because you're not usually using super wideband signals on HF anyway. But the highest sampling rate is 910 kilohertz complex, so it can easily grab all of any one HF amateur band with the exception of 10 meters. So I can receive an entire band at once and have multiple receivers running within that band. I have other, I do support other devices like the AMSAT UK FunCube, which is getting pretty old now. It's only got 192 kilohertz of bandwidth, but I have a whole bunch of them. We're planning to fly one on a balloon with a Raspberry Pi Zero, which is enough to handle it as part of a multi-channel FM repeater that I'll talk about later. And I also support the RTO SDR, very popular because it's only about, what, $25 or something like that. I don't think it performs as well as some of the others, but it's extremely inexpensive and therefore very, very popular. So I mentioned Radio D several times because this is the heart of the package. It's the biggest and it's the part that's taking the most work. Functionally, it's what's called a digital down converter, or DDC. Usually this function is done on a field programmable gate array. Most SDRs do it this way. I set out to show how much can be done without using an FPGA. Everything runs on a general purpose computer. In fact, it's not even using graphics processors. It's running on the main CPUs. And I think I've gone pretty far to show just how much you can do on a general purpose CPU doing a digital down converter. It uses a mechanism called fast convolution. I won't go into the math here, but it's based on a fast Fourier transform, which some of you may have heard of. Anybody who's ever used a radio with a waterfall display has used an FFT. In fact, if you've used a Wi-Fi device, you use an FFT. If you've used a mobile phone, you use an FFT. The point is that it's in everything now. And because it is so widely used, it has become very, very heavily optimized. There's some really good packages out there to do it, and it saved me a lot of work. And that is where most of the processing is in my package, is inside of this fast Fourier transform. But fortunately, I was able to use one that's open source at MIT that just works and works extremely well. I mean, I still can't believe how fast I can run this thing on a Raspberry Pi. I mean, this is well in the supercomputer territory not many years ago, and now you can run it on a Raspberry Pi, which, you know, used to be $35, but or $45, whatever, if you can get one. So the architecture of Radio D uses one big forward FFT that digitizes the entire input spectrum, which takes only 16% of a Pi 4 for the AirSpy R2 sampling about 9 megahertz of usable spectrum. I still think that's pretty amazing. And then for each channel that you want to demodulate, it uses one inverse fast Fourier transform. So you can think of this as, take a waterfall display on a radio, and then imagine peeling off a little piece or little pieces of that waterfall display, and then converting that back into a time domain signal, one you can listen to. That's not quite that simple, but it almost is that simple. So there's one big Fourier transform that takes the input data from the front end, very wideband, produces all of the waterfall channels, and then you have lots of little ones that take whatever piece you want and converts it back into audio, demodulates it, FM, AM, whatever you want, and sends it out. And because they work on fairly narrow bands, they use very little of the CPU. Each one uses about, I checked it last night, each channel uses about 1% of one core on a Raspberry Pi 4. That's when it's active. If it's inactive, it's less than that. I do some things to save CPU cycles when there's no signal. Each channel can come out either as a raw IAQ stream, or it can be demodulated with an FM demodulator, which has all the usual features. Has a tone squelch. It has even have threshold extension, which I've been playing with to work better, getting rid of popcorn noise at lower signal noise ratios. And it also has a wideband FM demodulator with a stereo decoder, which I've done all this from scratch myself. So yeah, I have one Pi 4 at home. Actually, I have several of them running at home, but the one that is demodulating the 70 centimeter band is right now demodulating 267 narrowband FM channels at the same time, with 39% of the CPU still idle. And if you run this on a x86 system, that's even lower. I mean, I mentioned the Pi 4 because, you know, it is was a relatively cheap system, and hopefully will be again. And it is actually fast enough to run all this stuff. So I've been actually running 3 of these for the last year, or actually last 2 years, recording, demodulating and recording everything I can hear on 2 meters, 125 centimeters, and 70 centimeters. I've got about 2 terabytes now of compressed recordings, and I have no idea what to do with it. So if anybody's got any ideas, I mean, one thing I could do that might make some people unhappy is to go through and find out just how much each of our channels is being used. There are an awful lot of repeaters around here that sit for weeks doing nothing but beaconing the time every hour, and then maybe see one QSO every week or so, with the CW ID, right? I mentioned Opus D as an example of another module that, because it's a very modular system, can convert PCM to Opus by compressing it. I mentioned Packet D, which can demodulate packet and APRS and APRS feed. I have a bunch of others, but I'm not going to go into too many more details here. I keep saying several times now that I'm not a user interface guy, but fortunately, turnkey boxes, things like APRS gateways, don't really require a user interface. You write a configuration file once, and then you just boot it up, and it just works. So I do have a very primitive text mode user interface just to use the protocol, demonstrate the protocol and exercise all the functionality. But I'm looking for people who like to do user interfaces to come along and write one for my package using my protocol. So the only two programs I have now are both text mode. I have control, which I use mainly in HF, because in VHF and UHF, where everything is channelized, I just have configuration files that list all the frequencies that I want to receive and where I want the data to come from and where I want it to go. So I use the control program really only occasionally on FM for debugging, like if I want to see, the signal-noise ratio in a channel or something like that. I use it interactively mainly in HF, but it will not, it will not look very impressive on HF versus, modern SDR, graphical SDR program like SDR Sharp. But again, it's not meant to compete with those. The monitor program will listen to an arbitrary number of audio streams at one time. And a couple months ago, we started talking about flying a repeater on a balloon at Mount Carmel High School. And I had this idea of building a repeater with multiple inputs feeding one output. And the idea was to prototype this and possibly fly it on the ISS. I mean, I do have that opportunity if I can show that this thing works. Because a single input FM repeater, it doesn't work very well in the ISS. If you ever try to use it, if two people key up at the same time, nobody gets through, unless you're at least 10 dB stronger than the sum of everybody else. So by having multiple inputs, and you can just pick one at random, I think there's a better chance of people getting through. If two people key up at the same time, you just hear two voices at once. And we're used to that in the Papa system, because if two people key up on different repeaters, you'll just hear the sum of their voices instead of a garbled mess. So it turns out all I had to do was to take the monitor program and add a hook to key the transmitter and another hook to do a CW ID, and it becomes a repeater controller. And it turned out to be really, really simple. So as I mentioned, it's open source. You can get it, and it's ready to be used by other developers, although it needs better user interfaces. But I will say that most fancy user interfaces are really not designed for more than one channel at a time. So you have to really rethink how you want a user interface to work. Do you really need one at all for many of the things that you can do with a multi-channel receiver? So here's some of the ideas at applications that I've been working on. Some of these I've already been doing. I mentioned the receive-only iGate that I've been running for several years. Another one that I'm getting increasing interest in is to be able to receive multiple National Weather Service radiosondes at once. They transmit in the 400 to 406 megahertz band, and lately, especially during these atmospheric river events, they've been flying several balloons at once or in rapid succession. And we've had a problem with each of the hilltop sites only being able to receive one or well, two if we have two SDRs at one time. And you can sometimes have, like, for example, the Toro Peak site can be off receiving one radiosonde while another one goes up and it misses it because it's busy with the first one. But my receiver is a natural for being able to receive any number of these at the same time. If I can get a wider band HF front end, like one that can grab the entire HF band from 3 to 30, or 0 to 30 megahertz, I'd like to be able to harvest everything. harvest every whisper frequency and every band, every FT8 transmission, high frequency data link, which is packet radio for commercial aircraft, and so forth, and any other mode you can think of. I also want to decode digital voice, but these can be extra modules that look at the output of the FM demodulator channels. This will be a separate module. I could probably adapt software like DVM to do this, although the proprietary codecs and DMR and D-Star and Fusion and P25 are a real headache. And here's one that I thought about recently. I haven't actually worked on this yet. I've been busy the last few months. But here's an idea I had, is a mobile voting receiver for PAPA users. Now, I don't know where you guys are and how, what kind of coverage you get from the PAPA repeaters, but in San Diego, where I am, there's no one PAPA repeater that is good everywhere. I mean, San Diego is just too hilly, and there's too many canyons. You're constantly changing frequencies to try to find the repeater that's best for you. So I had this idea, well, look, if I've got a receiver that can receive all the PAPA repeaters at once, well, just have it automatically pick whichever one is the strongest. You can do this every 20 milliseconds. The only problem I'll probably have with that is, I think Chris pointed out, is that the repeater's audio is not all exactly synchronized. So unless I take care of that, you're going to hear little timing jumps in the audio as it switches from one repeater to another. But it's still better, I think, than hearing a lot of mobile flutter, or just complete. Just squelch closing, you go down into a canyon. Yeah.
How does that proposed solution differ from what Chris has done with Mount Wilson, the V and W?
I don't know what you.
So that what you're talking about is a receiver into the repeater network. So there's actually two discrete receivers. Right. One's on Mount Wilson, the other's on Verdugo, and you steer that with what PO you transmit. I think what Phil is saying is that you, as the subscriber,
right,
use his module to listen to all of the repeaters.
Right. Put this in your car and listen to all the repeaters that you can hear at once, and have it pick the strongest one, and it tell you.
It's kind of like DMR roaming without the DMR.
Yeah. I mean, there are better ways of doing this in the long run, but given the analog system we have, I mean, actually it could even be done with digital. But given the analog system that we have, I think this is not a bad way to do it. Now, of course, if you're going to, if you're going to have just one receiver, you probably just listen to the 70 centimeter frequencies. In my area, the 220 frequencies are actually very good. In fact, I hear University City, I hear Toro Peak the best, believe it or not. So if you want to hear both bands, then you have to get two antennas and two front ends to do that. But it's entirely doable. So anyway, I thought this was a pretty cool idea, and I'm looking for other people to come up with clever uses for a receiver that can receive basically everything on a band at once.
I'd like to have one box that runs an iGate Broadcastify feed, an AIS feed, an ADS-B feed.
This will be ideal for Broadcastify. I mean, this could replace Broadcastify, right?
10 Raspberry Pi. Well, right now I'd like to just get them a feed without dedicating a receiver
for each channel, right? Well, the only requirement here is that whatever you want to receive will fit into the bandwidth of one of these things, and that will also control the amount of CPU power you need. As I said, I can demodulate I can grab 9 megahertz in about 2/3 of a Raspberry Pi 4. So the CPU usage will go up proportionally with that. And in fact, that CPU usage is constant whether or not there are any signals. Okay, so this is actually overkill. If you just want one signal at a time, like on HF, this is overkill. You're grabbing and processing all that data only to throw most of it away and look at a very small piece of it. So this thing is really, comes on its own when you want to receive lots of channels over the whole band at the same time. Okay.
Question.
Yeah.
Does the FCC use something like this?
Of course. I'm sure the NSA does. I mean, if I can do this on Raspberry Pi, right, the NSA has been doing this for decades. In fact, I know for sure that they have.
They probably have it.
I'm sure that they have. I mean, if anybody's heard of Edis Research, who were one of the earliest entries in the SDR field, run by Matt Edis, who I know. When I visited this factory, he showed me some of their special devices or special builds in the back room that had huge numbers of antenna inputs, and all he would tell me is for a government customer. So you can read on that whatever you want.
They have
You know.
antennas all over the country.
What's that?
They have antennas all over the country.
All over the world. All over the world.
Right.
I mean, years ago, back in the 90s, I was in Singapore on business, and I took a walk at night. And of course, Singapore being a city-state, you know, all the embassies are right there. I turned a corner, and there was the U.S. Embassy, and antennas just plastering the roof. And I just cracked up laughing, because they're not even subtle about it, right? Yeah. And that was in the 90s, so.
There's one on Saddle Peak near where we're at, which is what he's describing. So it can listen to the entire LA area, everything,
Sure.
everywhere, all at once.
Everything all at once, and we can do that. I mean, they obviously can. Okay, I mean that thing is about $169, and of course, you know, Raspberry Pi if you can get one. Although you can run it on any Linux machine. In fact, I was going to do this on a Raspberry Pi here, but I was having, well, I've got bit by the Achilles heel of a Raspberry Pi is it's very, very picky about its power source. So I instead switched to a laptop running Linux, and it actually is faster than the Raspberry Pi 4. It works fine. It's working fine here now, so I can do a demo. So I mentioned that you can use other front ends if you want. I mean, I mentioned the AirSpy only because I like it right now. There are probably other ones coming along. I'd be happy to use whatever's available and whatever's cheap. Yeah, I mentioned the R2 and the HF Plus. I checked, these are the prices of last night when I checked online, and the coverage. So that's it, except for a demo. Now I don't know if I should do the demo here or have people come up and look at it, because you know it can get kind of detailed. But I can at least show you what the programs look like. Let's see if I. Oh, good. I can get out of this, I think. Good. Okay. Now I'm going to. This is a window that I started up at home. And of course, you can't read it, but I'll blow it up in a second here. Let's see, Control plus. Whoops. There we go. That's my receiver at home. And the entries in bold are the ones that are currently on the air. Let me maximize the window here. There we go. And the S key automatically sorts. As you can see, on the right-hand side is activity, total, current, and idle. So the ones in bold are the ones that are currently on the air. Total is the number of seconds since the program started that channel has been active. Current is how long that repeater has, or that channel has been continuously, the squelch has been continuously open. And idle is the number of seconds since it was last heard. So not surprisingly, W6ZN 14528, which is almost always at the top of my list, that's active right now. If somebody wants to key up a Papa repeater, you can see what happens. Somebody key up a Papa system? Just kerchunk it. I'm sure nobody will mind. Oh, somebody just did. Okay, so I'm hearing Otay, Toro, Palomar, Sunset Ridge, Elsinore, I think. At least I think those are. I know they share frequencies. Okay, and it just dropped. Yeah. So okay, yeah. So what's interesting is when I listen to this, and I often just run this with all the channels going, and I don't know why I do this to myself, but it will on a stereo speaker. It will automatically pan the signals across the stereo spectrum, which is it's not an idea that's new with me, but I understand. Some audio panels on airplanes do this because you often have multiple radios, and it's less confusing to the pilot if they can, if the different radios seem to be coming from different places in their stereo spectrum. But especially when I listen to the Papa system or any other network system, it's like listening to people talking in a stadium, because of the slightly different delays between all of the repeaters. Also, there are different delays in my own system, which is
Sounds like some
details.
kind of radio dystopian hell.
Yeah, but I can mute the ones I don't want. Most of the time, if I want to actually listen to the Papa system, I'll just mute all but the strongest one. And at home, I can hear about half a dozen, full quieting. It's only in the car, that I can't really find one that is good all the time as I drive around.
So the 2 terabyte cache of data that you've amassed over the years includes all this, or is the Papa system just a small part of that?
Papa is just a small part. It's everything. The 2 terabytes is everything that I've collected in the last, it's about January of 2021.
Would it be possible to separate out the Papa data and then maybe look at trends?
Oh, sure, sure.
Which of the
Yeah,
Papa
each one is stored. Each one is stored as a separate file. What I do it is it's structured by directory. This for frequency, and then with it, and each file is time stamped, and it automatically gets rid of if the squelch closes, it gets rid of the silence. It will keep recording for up to 20 seconds. And if there's nothing at the end of that 20 seconds, it'll just edit out the last 20 seconds of silence. But otherwise, you'll hear it in real time, including the pauses.
Yeah, if you could derive trends from that.
Oh, yeah,
that
sure.
would be helpful for him to plan the system.
Sure.
To see geographically which directions
Yeah.
have more demand.
Yeah, you're welcome. You're welcome to it. Now everybody's chucking all their favorite repeaters. Huh? Yeah. So yeah, you definitely see patterns, and believe me, there are some channels that are a lot busier than others. I've noticed this for a long time. You can see there's just in the amount of disk space is used by each directory for each frequency. I do have this running here locally on this laptop over here, which is running Linux. Everybody's heard an FM receiver before, so it's not particularly exciting. But if I bring up this window, which is my local monitor program.
Thing so you can see everything that's going on.
Yeah.
There's activity over here. I'll go talk on that.
Yeah. All right. Okay.
Only if you're in range of the repeater.
Well, yes.
Well,
Sure.
otherwise, who cares?
Okay, I'll blow this up a little more because
Right?
there's only one entry here. Let's see if this still works. KA9Q testing, 1, 2, 3, 4, 5. Okay, and I actually have 2 monitors going, which is why you heard an echo. Now I made it a little larger because there's only one entry, so you can see them all. This is the frequency. This program has a tone detector. It looks for every PL tone, including some that aren't very common. And it automatically notches them out once it finds them. So when it first sees a tone, it will tell you what that tone is, and then it'll turn on a notch and keep that notch in place, because otherwise you hear a burst of tone at the beginning of each transmission, which is a little bit annoying. So it'll keep that notch on until you reset it or a different frequency is detected. I have a table, which you saw on the other screen. It's just a lookup table. Looks up the channel ID in the file and displays it from a table. It's kind of primitive. What I'd really like to do is take the repeater directory, suck it in to my database, and then find the one that is nearest me with the same PL tone and display that one. That would actually be nice. On the left-hand side, where it says dB and pan, dB is just a volume control. I can mute individual entries or adjust the volume up and down. And pan is that stereo pan I talked about, where I can place it left or right in the stereo spectrum. So that's the control program. I can show you, that's the monitor program. I can show you the control program, but like I said, I don't use this one very much on VHF and UHF, only on HF. And where it's not going to be very impressive because programs like SDR Sharp with waterfalls and so forth do a much more impressive job. But this is like everything you ever wanted to know if you're debugging this thing. And I'm not going to go through this, but everything you ever want to see is in here. All the signal levels, and it computes the signal noise ratio in each channel. That's how I do the squelch. So that can be used for a voting system. One classic way you do a voting system is you look for the quietest signal but that assumes that the audio levels are all matched. But you don't have to assume that if you actually looking at the IF signal noise ratio, which is how I will probably make that voting receiver work. So yeah, I'm not going to go on all this to just bore people, but basically everything you ever want to know about the internals of the receiver is all here. Yeah.
It'd be tough to get that on a typical GUI, all that stuff.
Yeah, well, hey, my philosophy about user interfaces is that nobody should have to use any of this stuff just to make it work, do something simple. But everything should be available if you really want to go in there. Like, I mean, some of my earliest memories are playing around with my dad's stereo and wondering what was behind the knobs.
Yeah.
God, it drove me nuts. I wanted to know what was behind the knobs. One of the reasons I became a ham, right, was to understood how radios work behind the knobs. But you shouldn't have to know that just to turn on the radio and listen to something.